Hi everyone, I'm Alex Wein, and this is joint work with Justin Holmgren at NTT Research, and I'll be talking about counterexamples to the low-degree conjecture. So I want to talk about a class of problems called high-dimensional testing problems, and to illustrate this by way of example, one canonical problem in this class is called planted clique. So in the planted clique problem, the goal is to distinguish between two distributions. In the null distribution Q, I give you just a random graph with n vertices and each edge occurs with probability 1/2. In the planted distribution P, I give you a random graph with a planted k-clique. So a k-clique means I've chosen k vertices at random and connected them all to each other, like the ones shown in red here. And so I give you a graph from one of these two distributions. Your goal is to decide which one it came from, and you would like to succeed with probability tending to 1 as n goes to infinity. There are also all sorts of other high-dimensional testing problems. So typically these have some kind of a planted signal buried in some kind of noise, and the goal is to detect the presence of this signal. Decide whether it's there or not. And one feature of these types of problems is what we call statistical to computational gaps. So again, in the planted clique example, as k, the size of the clique, gets bigger, this problem goes through 3 different phases. So when the clique is too small, the problem is simply statistically impossible. You can't tell whether or not there was a planted clique. On the other hand, if k is quite big, bigger than squared n, the problem is easy, meaning there is a polynomial time algorithm to detect the presence of a clique of that size. But in the middle, we have this conjectured hard regime, meaning that the problem is statistically possible if you're willing to check all the possible cliques, but we don't know a polynomial time algorithm. And we kind of believe this is fundamental, that really no polynomial time algorithm should exist, but we don't know how to actually prove this, even assuming p not equal np or some kind of standard assumption from complexity theory. So instead, we often try to give some kind of formal evidence for why we believe the problem is hard. And this can take a few different forms. So for example, average case reductions. If you believe planted clique is hard, you could use this to prove that certain other problems are hard. There's also sum of squares, lower bounds, or other lower bounds against certain classes of algorithms, and so on. But today I want to focus on a particular framework based on low-degree polynomials, which I'll describe in a second. So these low-degree algorithms. So this idea is inspired by a line of work on sum of squares by these authors here. And the idea is quite simple. A low-degree algorithm is just a multivariate polynomial that takes in your whole input and outputs one number. So for example, if your input is a random graph, then there will be n choose 2 variables, one for each edge. Maybe they're 0, 1 valued. And you get to take any polynomial you like in all of these variables that just outputs one number. And when I say low degree, I mean degree logarithmic in n. And so what does it mean for such a polynomial to succeed at testing? Well, here's one such definition. So I'm requiring that in the null distribution, the polynomial has expectation 0, whereas in the planted distribution it has expectation 1. And in both cases, it has variance little o of 1. And so by Chebyshev's inequality, you can threshold this polynomial to decide reliably whether the input y came from q or p. Okay, and what's quite nice about this particular formulation, this definition of success, is that it's actually tractable to analyze. So for upper bounds, we can often construct a polynomial that succeeds in this sense. And for lower bounds, we can prove that no such polynomial exists. And for the lower bounds, we actually prove something a bit stronger, that even the first three conditions here cannot be achieved, ignoring the one in red. And so, for example, it's now known that for the planted clique problem, low-degree algorithms succeed in the conjectured, well, in the easy regime where we know that algorithms succeed, and they fail in the conjectured hard regime. And this is not specific to planted clique. Actually, for all sorts of different problems, we now sort of believe that polynomials of degree order log n are as powerful as all known polynomial time algorithms. So this has now been observed to be true in planted clique, sparse BCA, etc. All these problems I listed at the beginning. And so maybe we wonder, why? So one explanation is that, well, for these testing problems, often the best known algorithm takes the form of some kind of spectral method, meaning you threshold the leading eigenvalue of some matrix that you build based on your input. And using power iteration, you can typically implement such an algorithm as a logarithmic degree polynomial. And then conversely, well, it's not true that every logarithmic degree polynomial can actually be evaluated in polynomial time. It turns out that for these examples that we know of, whenever there is a log degree polynomial that succeeds, there is also a spectral method or some kind of polynomial time algorithm that works. And so this is quite nice. It lets us predict fairly easily when various problems should be easy, when they should be hard, and give some kind of concrete evidence for what makes the hard regime hard. And this is somewhat more straightforward than proving, say, a sum of squares lower bounds or an average case reduction. And as a result, this method is applicable to a somewhat broader class of problems. Okay, but I've written here that this conjecture is for natural problems. So of course, there's some limits to the class of problems where this holds. One counterexample is the planted 3 XOR problem. This means that I give you a 3 XOR formula, and your goal is to decide whether or not there's a planted satisfying assignment. And so in reality, you can always check in polynomial time whether there's a satisfying assignment just by running Gaussian elimination. But low degree polynomials cannot implement Gaussian elimination, and in fact, do not succeed at this problem unless the number of clauses is above a certain limit. But the low degree prediction is not completely wrong here, because Gaussian elimination is a very brittle algorithm. And if we add just a small amount of noise to our XOR problem by flipping a few of the clauses so that there is no longer a satisfying assignment, then Gaussian elimination breaks down completely. And now the best known algorithms actually coincide with what low degree polynomials can achieve. And so we'd like to really formalize this meaning of natural. What exactly is the class of problems where we believe low degree algorithms are optimal among all polynomial time algorithms? Okay, so the first attempt at formally writing down a version of this low degree conjecture was by Sam Hopkins in his PhD thesis. And so this is kind of an informal statement of his formal conjecture, but these are the main features. So we will assume that Q has IID entries and that P is highly symmetric. So for example, in planted clique, the whole distribution is symmetric with respect to permutations of the vertices. And furthermore, we'll assume that logarithmic degree polynomials cannot distinguish these two distributions in the sense that I described earlier. So under these assumptions, the conclusion is that no polynomial time algorithm can distinguish between Q and a noisy version of P. So here this noise operator is defined as follows. For each entry, with some probability delta, you just resample that entry from whatever the entry-wise distribution of Q is. And the purpose of this is just to add a little bit of noise in order to rule out any of these brittle algorithms like Gaussian elimination for the XOR case. And so this symmetry assumption, so it's typical in these high-dimensional testing problems to have a lot of symmetry. But one question is, is this assumption actually needed in order to make the conjecture true? So it's kind of not clear a priori. Okay, so let's talk about our contributions. So we actually refute the conjecture of Hopkins, and we do this in the case where Q is IID Gaussian. And so our counterexample feels maybe a bit like cheating. It crucially exploits the fact that we can take some real number and use its binary expansion to encode a whole bunch of data. And we know that the noise operator will leave many of these real numbers untouched, and so all of this data will be there. But there's a fairly simple fix, so a way to modify the conjecture so that we no longer know how to refute it. And this is by changing the noise operator a bit. So instead of using a noise operator that resamples a few entries, really you should use a noise operator that slightly corrupts every entry. And the reason for this is that it destroys all the low order bits in the binary expansion and would prevent us from doing this kind of trick. Our second contribution is to show that the symmetry assumption is necessary in some sense, meaning that if we drop the symmetry assumption completely, then there is also a counterexample. And this is in the case where Q is IID Bernoulli. And so together, these results somewhat refine our understanding of what types of problems we expect low-degree algorithms to be optimal for. So let me tell you a bit about how to prove such a thing. So let's first prove the second claim, which is that the symmetry assumption is necessary. So to recap a little bit what the goal is, we want to construct these distributions Q and P. In this case, it's going to be over 0, 1 to the n with the following properties. So Q is going to be just IID, and then we want no low-degree algorithm to be able to distinguish Q and P, but we want some polynomial time algorithm to distinguish Q from a noisy version of P. All right, so how do we do this? So the construction is that Q will just be simply a random bit string, and P is going to be a random code word from a certain error correcting code. And well, why does this help? So there's a few properties of the code that we're going to need to use. So the first one is that code words are d-wise independent for d order n. And so what this means is that if I pick a random code word, but I just restrict my attention to only d bits and look at the resulting marginal distribution there, it just looks like a uniformly random bit string. Right, and so a consequence of this is that any degree d polynomial has the same expectation under P as under Q. And so degree d polynomials cannot distinguish the two distributions. And another important property of the code is that it comes with a decoding algorithm. That so say there's some code word and some delta fraction of the bits get flipped. This decoding algorithm can still take this noisy code word and recover the original code word. And so this gives a polynomial time algorithm to distinguish Q from the noisy version of P. Right, so how does it do this? Well, it just tries running the decoding algorithm. And so if the data came from P, we have sort of a noisy code word, and the decoder can decode this to get back the true code word. On the other hand, if the input came from Q, then when you try running the decoder, it will fail because there simply is not a nearby code word. So that proves the first claim about the symmetry. Now, in order to actually refute the conjecture, we need to make the distributions symmetric somehow. So we'd now like to construct permutation symmetric distributions, Q and P, meaning they're unchanged by any permutation of the coordinates. And these are now going to be distributions over R to the n. And we want sort of the same properties. Q is just going to be IID, IID Gaussian. And no low degree algorithm can distinguish Q from P, but some polynomial time algorithm can distinguish Q from noisy version of P. Okay, so basically we use the same construction as before, but now we need to do something to make the distributions symmetric. So here's the main idea. So instead of observing just a bit string, we are now going to imagine observing a list of these pairs I comma x sub I. So we're kind of like giving you the bits in some random order, but each one is sort of tagged by its position in the original string. And then this whole pair, I comma xi, is going to be encoded by a single real number as just a single entry of our distribution. And then there's a few technical things to deal with here. Of course, there could be some conflicting information if the same I gets chosen twice, and we'll actually just throw that out. And so I won't show you the full details of this, but essentially the same argument goes through, but now the error correcting code now needs to handle erasures as well as errors. So erasures meaning that some bits simply were not observed at all. So this occurs either when this conflicting information is thrown out, or if by chance some I values simply do not get sampled by this random procedure, you do not observe all of the bits. All right, so that's basically the idea of the proof. Let me just summarize a bit to wrap up. So the goal here was to try to formalize the class of problems for which we believe low degree polynomials are optimal among all polynomial time algorithms. And so we made a few contributions along these lines. We refuted this conjecture of Hopkins and pointed out that the noise operator really should be defined a bit differently. And we also showed that the symmetry assumption is necessary. A few future directions along these lines. We can ask exactly how much symmetry is necessary. And also more broadly speaking, it would be nice if this low degree conjecture could find applications in other areas of computer science, such as cryptography. Finally, if you want to know more about this low degree method for predicting computational thresholds, here's a survey article that you could take a look at. All right, thanks a lot for your attention.